Here, let's look at the measures of variation for types of data. So in other words, how much does our data vary from one another? So consider the two sets of data, dataset 1 and dataset 2, where dataset 1 is just given by 36, 40, and 41. And let's say these represent ages of 3 random people at Starbucks. So 36 years old, 40, and 41 years old. Very, very close together in age are these 3 people in dataset 1. And dataset 2 has 2, 40, and 75. So a 2-year-old, a 40-year-old, and a 75-year-old, very different spread of data here in dataset 2 compared to dataset 1. Interestingly, when we look at the mean for each of these data sets, we get the same number. We get 39. So if you add up 36 plus 40 plus 41 and divide by 3, you should get 39. So the mean for data set 1 is the same as it is for data set 2. 2 plus 40 plus 75 divided by 3 is also 39. And the median for each one of these data sets is also the same. It's also 40. So just finding the average or the median, or the mean, I'm sorry, and finding the median doesn't really describe what's happening here with how much the data here or the ages are varying in each data set. So that's what we're going to look at in this video is descriptions of variation. The first type of variation we're going to look at is called the standard deviation. The standard deviation of sample values is a measure of how far the data values are from the mean of the data. So if you look at these two, let's say these are grades on an exam in 2 classes. So here's one instructor's class. The grades on this exam are really spread out. There's somebody got, let's see, it looks like it's out of 150 points here. So somebody got, let's say, oh, I said it's IQ score. Sorry, pretend they're grades. Somebody got a 58, it looks like, and a couple people got 130 points. A really wide spread of data values compared to this other sample where they're grouped together all in the middle. So pretty much everybody in the second class got the similar scores to each other. So we would expect the standard deviation or the measure of how far away each data value is from the mean or from the middle, the standard deviation would be bigger in this spread out data set, and the standard deviation or how far away the data values are from the center would be smaller in this very closely clustered data set here. So that's what standard deviation is going to measure. Let me show you the formula for the standard deviation. And I'm sorry, I know it looks complicated. You're going to be doing this a lot. You're going to get used to it. And I have a couple of shortcut formulas for you too. So the formula for standard deviation, we're going to use S to denote standard deviation for a sample. So a small sample, smaller than an entire population. We're going to use S for standard deviation. And we take the square root of the sum of all of the data values minus their mean, square that, and then add all those values up, excuse me, divided by n minus 1. So it's a little complicated, but I think you'll get the hang of it. So let's try this. Let's just do with 3 data points. Calculate the standard deviation for the numbers 1, 3, and 14. So the first thing that we need to find is the mean. That's the first thing that we need to find. So the mean of the numbers 1, 3, and 14, add them together and divide by 3, gives us 6. So to calculate the standard deviation, we're going to take 1, our first data point, minus 6, square it. And then we're finding the sum of all these. The second data point is 3. So 3 minus the mean, so 3 minus 6, square that. And then add to that the last data point, 14 minus 6, and square that. And then divide by the total number of data points minus 1. So 3 minus 1. Okay, PEMDAS, order of operations, we need to do parentheses first. So let's see, 1 minus 6 is negative 5, squared is 25. 3 minus 6 is negative 3, squared is 9. 14 minus 6 is 8, squared is 10, and may as well do 3 minus 1 is 2. Okay, add all those up, we get 98 divided by 2. I chose one that was easy on the brain and just squared of 49. So our standard deviation here is 7. Okay, let me show you. It doesn't look like it's a shortcut formula, I know, but it is a shortcut formula for standard deviation. Gets you the same result as on the previous formula. What I want to point out here is, even though this looks uglier, we don't have to calculate the mean here. There's no x bar anywhere in here. So this is how you would use this formula. It's a square root of the number of data points times the sum of their squares minus the sum of the data points and that number all squared. We divided by the number of data points times that number minus 1. So let's practice it with the previous example. So again, we'll use the shortcut formula to calculate the standard deviation for the numbers 1, 3, and 14. Okay, so again, we don't need to find the mean for this one, which is kind of nice. So we'll take n, the number of data points, which is 3, and then multiply that by 1 squared plus 3 squared plus 14 squared. 1 squared plus 3 squared plus 14 squared. And then subtract the sum of those numbers, that sum squared. So 1 plus 3 plus 14 all squared. Divided by n is 3, and n minus 1 will be 2. Okay, be very careful with your order of operations here. So I'm going to do parentheses first. And in the first set of parentheses, I'm going to square those numbers. So 1 plus 9 plus 14 squared is 196. But in the second set of parentheses or brackets, we have to add first, because that's inside the parentheses, before we can square. So 1 plus 3 plus 14 is 18, and then we'll square that number. Okay, so let's see. When we do 1 plus 9 plus 196, we get 206 times 3. And then 18 squared is 324. So we have 294 divided by 6, again, which is 49. Remember, it gives us the same result as we had in the last one, or 7. So it doesn't matter which formula you choose to use for standard deviation, this one or the previous one, they'll both give you the same result. You pick whichever one you like. Okay, if you have the standard deviation of an entire population, then we use a slightly different notation. We use the Greek letter, this little Greek letter for S. We use this a little lowercase sigma. Mu is the mean for the population. So it's mu is akin to x bar here. And the big difference is we're going to divide by the total number of data points in the population, not the sample size minus 1. That's the big difference for a population. Okay, the range rule of thumb. The range rule of thumb tells us how to find usual or unusual values given a data set. So if we have a range rule of thumb, for the range rule of thumb, if we have the mean, the minimum usual value should be the mean, or the average, minus 2 standard deviations. And the maximum usual value should be the mean plus 2 standard deviations. Anything outside of that range is going to be considered unusual. This is really cool. We can use statistics to tell whether some data point is usual or unusual. So let's try this example. The mean score on an exam was 84%, and the standard deviation was 6. If Alec got a 99% on the exam, is this an unusual score? Okay, so let's calculate this. The maximum usual value was the mean, so 84, plus 2 standard deviations. So 2 times 6. So 84 plus 12 is 96. That means that Alec's score was unusual of 99. If I ask the question, if Alex got an 85 on the next exam, is this an unusual score? I don't know. I have to know the mean score on that exam. I have to know the standard deviation score for that exam. I have no information on how everybody else performed on that exam, so I can't answer the second question. So in order to find the usual or unusual values, you have to know the mean and you have to know the standard deviation. Okay, another way to state this is to say that most data, 95% of the data, will lie within 2 standard deviations from the mean. So let's say you're looking at FICO credit scores. And we have a sample of 1, 2, 3, 4, 5, 6, 7 FICO credit scores, 500, 680, 685, 690, 693, 694, and 740. And we just want to figure out what is unusual or usual. Now, by now, we should all be comfortable calculating the mean. So in order to tell, remember, usual or unusual, we need to know the mean and we need to know the standard deviation. So we're going to find the mean. We're going to add up all the scores and divide by 7, and we should get 668.9. And if we use that lovely formula from the beginning of this video to find the standard deviation, we should get 77.1. So most data should be between 514.8 and 823. So let's look at how I got those numbers. The low number, 514, is 2 standard deviations away from the mean. So 2 times 77.1, if we subtract that from the mean, we get 514.8. And 2 standard deviations, if we add that to the mean, we should get 823. And if you look at these numbers here, no FICO score listed on this set is larger than 823, so that certainly fits. And only one number is smaller than 514, so most of the data here is within 2 standard deviations from the mean. Another way to say this is, for a bell-shaped data set, we have what we call an empirical rule. So this is just really cool. About 68% of all the data will fall within 1 standard deviation from the mean for bell-shaped data. 95% falls within 2 standard deviations from the mean. That's what we just looked at. And 99.7% of the data will fall within 3 standard deviations of the mean. And if I were to draw a picture of this, here is some data that's bell-shaped. Nice bell-shaped stuff. That bell-shaped data set. Here's the mean in the middle. 68% of the data, the vast majority of the data, is within 1 standard deviation from that mean. If you add a little bit extra, here's 2 standard deviations. 95% of the area under this bell-shaped data curve falls within 2 standard deviations from this mean in the middle. And 99.7% of the data falls within 3 standard deviations from the mean. And only a little bit, 0.1%, falls outside outside of 3 standard deviations above or 3 standard deviations below the mean. That's pretty cool.